Hi friends, my name is Narsimha and I'm studying my BTech in Institute of Aeronautical Engineering College. Today, as a part of my AIT Tech Talk videos in the subject of Theory of Computations, I want to explain about a topic named the graph isomorphism problem. So, if you have gone through the graph theory or graphs or data structure subject, you can have an idea of what is graph and how to build a graph and how to analyze a graph and how to perform operations on a graph. So in this topic, in this today video, I want to explain about graph isomorphism problem. Introduction. The graph isomorphism problem is the computational problem of determining whether two finite graphs are isomorphic. The problem is not known to be solvable in polynomial time nor to be NP complete, and therefore may be in the computational complexity class NP intermediate. So this graph isomorphism problem is the main motto is it is used for determining whether two finite graphs are isomorphic or not. The problem is not known to be solvable in polynomial time. Means the actual accurate period of time in the finite number of time it cannot be solved. It is known that the graph isomorphism problem is in the low hierarchy of class NP, which implies that it is not NP complete unless the polynomial time hierarchy collapses to its second level. At the same time, isomorphism for many special classes of graphs can be solved in polynomial time. And in practice, graph isomorphism can often be solved efficiently. Next, this problem is a special case of subgraph isomorphism problem, which asks whether when graph G contains a subgraph that is isomorphic to another given graph H or not. This problem is known to be NP complete. It is also known to be special case of the non-abelian hidden subgraph problem over a symmetric group. Next, in the area of image recognition, it is known as the exact graph matching. The graph isomorphism problem is computationally equivalent to the problem of computing the automorphism group of graph and is weaker than the permutation graph isomorphism problem and the permutation graph intersecting problem. Once have a look of this, and after that I will explain what is NP complete. So here a problem is called NP complete non-deterministic polynomial if its solution can be guessed and verified in polynomial time. Non-deterministic means that no particular rule is followed to make the guess. If a problem is NP and all other NP problems are polynomial time reducible to it, then the problem is NP complete. So if there is a problem, means for example, there are many problems in maths which have been not solved up till due date, but the solution is given. So if it is guessed, the answer is guessed, and there is no particular law or a particular theoretical manner is used or any theorem is used, then it is known as NP complete. Next, solve special cases. So by using this formula, what are the applications or the special cases solved by using this? A number of important special cases of the graph isomorphism problem have efficient polynomial time solutions such as trees, planar graphs, interval graphs, permutation graphs, circulant graphs, bounded parametric graphs. So these graphs can be constructed by using the coding process. By if we know data structures that stacks or queues, then it will be very useful for you to know. Next, graph for continuation of the other slides, graphs of bounded tree width, graphs of bounded genus, graphs of bounded degree, graphs with bounded eigenvalue multiplexity. These eigenvalues can be known in the matrix operations. K contrastable graphs, a generalization of bounded graph degree and bounded genus, and color preserving isomorphism of colored graphs with a bounded color multiplexity. Next, this is the actual graph representation, that is the vertices will show the data and the edges between the vertices will show the connection and the relationship between two data or two vertices. These are graph G, graph H, and isomorphism between G and H. Here there are 8 vertices, that's A, B, C, D, E, the G, H, I, J. In the graph H, we have 1, 2, 3, 4, 5, 6, 7, 8. And the two graphs are very different. F of A is equals to 1, F of B is equals to 6, and F of C is equals to 8, F of D is equals to 3, F of G is equals to 5, and F of H is equals to 2, F of I is equals to 4, and F of J is equals to 7. Means the number of connections between that and how they are built are known in this isomorphism between G and H. So next, Because here f of a is equals to 1, f of b is equals to 6, and f of c is equals to 8. Here we can see the connections and the relationship between two vertices of different graphs. So these two are finite graphs, means finite number of vertices are there. So in these finite graphs, whether these two are polymorphism or not can be known, isomorphic or not. Complexity class GI. Since the graph isomorphism, GI means graph isomorphism, since the graph isomorphism problem is neither known to be NP complete nor known to be traceable, researchers have sought to gain insight into the problem by defining a new graph isomorphism. The set of problems with a polynomial time Turing deduction to the graph isomorphism problem. Because this graph isomorphism is neither means not NP complete or not tractable. So this is known. If in fact the graph isomorphism problem is solvable in polynomial time, GI would equal to P. On the other hand, the problem is NP complete, GI will be equal to NP, and all problems in NP would be solvable in quasi polynomial time. So there are two cases. In first case, if the graph isomorphism problem is solved in polynomial time, GI will be equals to P. In other case, if it not solved in polynomial time, if it is completed in NP complete, then it is GI will be equals to NP. And all other problems in NP would be solvable in quasi polynomial time. Next, as is common for complexity classes within the polynomial time hierarchy, a problem is called GI hard, means graph isomorphism hard, if there is a polynomial time Turing deduction from any problem in GI to that problem. That is, a polynomial time solution to a GI hard problem would yield a polynomial time solution to the graph isomorphism problem, and also all problems in GI. The graph isomorphism problem is contained in both NP and COAM. GI is contained in and low for parity P, as well as contained in the potentially much smaller class SPP. That it lies in parity P means that the graph isomorphism problem is no harder than determining whether a polynomial time non-deterministic Turing machine has an even or odd number of accepting paths. J is also contained in and low for ZPP-NP. This essentially means that an effective Las Vegas algorithm with access to an NP oracle can solve graph isomorphism so easily that it gains no power from being given the ability to do so in constant time. Next, problem checking. Suppose P is an claimed polynomial time procedure that checks if two graphs are isomorphic, but it is not trusted. So there is an example P, which will be same as graph isomorphism, but is not trusted. To check if graphs G and H are isomorphism, ask P whether G and H are isomorphism. If the answer is yes, attempt to construct an isomorphic using P as subroutine, means an theory, means theorem. Mark a virtue, means vertex U in G and V in H, and modify the graphs to make them distinctive with a small local change. Ask P if the modified graphs are isomorphic. If no, change V to a different vertex. Continue searching. Either the isomorphism will be found and can be verified, or P will contradict itself. If the answer is no, perform the following 100 times. Choose randomly G or H and randomly permute its vertices. Ask P if the graph is isomorphic to G and H. As in AM protocol for graph non-isomorphic, if any of the tests are failed, judge P as invalid program. Otherwise, answer no. These are the test cases. As we will do right in Python if or else cases. The same way, if the answer is yes, then we have to do the attempt of construction of isomorphic using P as subroutine. If answer is no, we have to perform 100 times and check for the answer. Next, this procedure is polynomial time and gives the correct answer if P is a correct program for graph isomorphism. If P is not a correct program but answers correctly on G and H, the checker will either give the correct answer or detect invalid behavior of P. If P is not a correct program and answers incorrectly on G and H, the checker will detect invalid behavior of P with high probability or answer wrong with probability 2 to 100. Notably, P is used only as black box. Applications means the use where this graph isomorphic problem will be used. Graphs are commonly used to encode structural information in many fields, including computer vision and pattern recognition and graph matching, that is identification of similarities between graphs, is an important tools in these areas. In these areas, graph isomorphism problem is known as the exact graph matching. In Cheminformatics and in mathematical chemistry, graph isomorphism testing is used to identify a chemical compound within a chemical database. Also, in organic mathematical chemistry, graph isomorphism testing is useful for generation of molecular graphs and for computer synthesis. Chemical database search is an example of graphical data mining where the graph canonization approach is often used. In particular, a number of identifiers for chemical substances such as smiles and INGs designed to provide a standard and human readable way to encode molecular information and to facilitate the search for such information in databases and on the web. Use canonization step in their computation, which is essentially the canonization of the graph, which represents the molecule. In electronic design automation, graph isomorphism is the basis of the layout versus schematic circuit design step, which is an verification whether the electric circuits represented by a circuit schematic and an integrated circuit layout are the same. So in this application, the main way where it is used is in the chemical in chemistry industry, because the mathematical chemistry, that is the molecular formula or in theorem or in a graph representation or getting the distance between two vertices or getting the distance between the vertices and how to store the data and how to divide the whole parts of the data into subparts and how to do the work. So this is about my lecture, and thank you friends. I hope my lecture is useful for you, and thanks for watching. Thank you.